Hello everyone, welcome to our presentation on wind turbine permanent magnet synchronous generator control strategy by Axel Rios.
And Pasquale De Luca. So, wind power is one of the most pivotal roles in reducing our nation's carbon emissions, and it is a very versatile and a very efficient form of power generation. Is in many places of the world, there's wind blowing all the time, and they make up a huge part of our nation's power grid. So before we can start talking about the specifics of each turbine, we have to kind of preface this with what each type of turbine is. So we have type 1, 2, 3, and 4 turbines. Now, throughout the years, each of these turbines have been iterated on and added to refine the processes that can convert wind power into electrical power. So the oldest design is type 1, and these are directly connected to the grid and have a fixed speed. So if you have a wind speed that's slightly faster or lower, you're not going to be generating optimal power. Now type 2, this was developed later on, and it includes a little bit more variability, so its Pmax includes a wider range of wind speeds. Now, type 3 is the most commonly used type of turbine configuration. These are known as deep fed or doubly fed induction generators. Now, its generating range is much larger than 1 and 2 and includes a wide variety. It's very versatile, and it's why it's the most commonly used. Now, for type 4 generators, this is what we're kind of going to be referencing as we progress into the slides. Here, the gearbox is removed and it is coupled with an electric or permanent magnet.
So we'll be going to talk about the advantages of the type 4 um, turbine involving the permanent magnet synchronous generator. So it has higher efficiency. So it has higher efficiency due to the elimination of a DC supply, and therefore we don't need to rectify it from the grid to the generator. Therefore, we have more reliability in the wind turbine operations. And also, one of the great advantages to this is that we remove the gearbox. Removing the gearbox, we eliminate mechanical losses and we improve the lifespan of the wind turbine system.
So perfecting angular motion is important to generating effective power, or power that matches the grid. And we're able to do this with pitch control and yaw control. So the goal of this is to spin the blades of the rotor in order to generate a frequency and power output that matches the grid. And so if you have, let's say this is your rotor, and you have wind hitting it at this angle, and you change that angle to this, that is going to spin the blades slower or faster. Now, that is what we call pitch control. Now, when we're referring to yaw control, we're spinning the entire turbine to either face away from the wind or towards it. Now, using these methods, we can determine or we can generate effective power with a wide variety of wind speeds.
So when designing the wind turbine, it's important to consider what range of TSR you want to operate in. So a TSR is tip speed ratio. It is the ratio of blade speed over wind speed. So this parameter is important to ensuring efficient energy production and turbine performance. So when we have a high TSR, a TSR greater than 1, that tells us that the blade is going faster than the wind. And when that happens, that means that we are capturing the same wind energy, and therefore we won't be producing any mechanical torque, and therefore it will not be efficient. When we have a low TSR, less than 1, that means our blade is going so slow compared to the wind, and we are missing the wind. We're not capturing an efficient amount of wind in order to be operating at our ideal maximum point. Another point parameter is power coefficient. So power coefficient uh, is the ratio is a ratio of mechanical power over wind power. It's always going to be less than 1, but it's important. It's important as it tells us how much energy is actually being transferred to mechanical. And so this ratio will change as we vary the TSR. And so when we have a low TSR, we can have a low power coefficient, and that cause that tells us that we have a low mechanical power output, which is not efficient. And when we have a too high TSR, that means that we are also at a not efficient point as we have low mechanical power. But when we go varying it around, there is a maximum ideal point where we get peak mechanical power, and there's a relationship with power coefficient with torque coefficient using the TSR. And so essentially at a certain TSR, there will be a peak coefficient for power and torque, and that tells us we will have a maximum torque and a maximum power output.
So in order to ensure that we are generating maximum power, we use control strategies to determine where we should be in a system. So there's a lot of challenges that can occur when you're finding your Pmax. There are wind speed, variation, turbulence. There's the the rust on any sort of mechanical errors which can occur. And all of these can come into play when you're performing these calculations. And to perform them live in real time is too constraining on the machines that you're performing these calculations on. So what is done instead is you're taking a bunch of different potential Pmaxes at different wind speeds, and you're able to then match up that graph with what your wind speed is reading. And so then what we're able to do is we're able to balance Q and D axis currents based on whatever curve we have chosen. And this is supposed to maintain grid stability and optimize the generation that we're putting out to the grid.
So permanent magnet synchronous generator technology is making advancements, and it is seen in the market as efficient and reliable renewable energy solution. It's important to dive more deep into this application as it can allow um, it can allow great usage for sustainable power grids and improving the performance of wind turbines.